Good afternoon, everyone, and welcome to Building Reactive Services with Functional Programming. I'm Rachel Reese. So today I'm obviously going to speak on the reactive services, and by this I mean generally services that adhere to the guidelines laid down by the Reactive Manifesto. And this is a technique that we use a lot at jet.com where I work, and so a quick spiel about us. We are taking on Amazon. We launched last year. We're a startup. We aren't actually available in Australia, but we'll hire Australians. But we have over 20,000 orders per day. Our Apple and Android apps were rated really, really highly. 600,000 first-time buyers in our first, I think that was our first 2 or 3 months. So we use a lot of technologies. We're very much a right tool for the job kind of company. We are very heavy users of Azure. And in case you noticed, we are very heavy users of Azure because we are taking on Amazon. So we are very much not heavy users of AWS. But we use VMs, the DNS, SQL Azure, Active Directory. We use a lot of the Azure technologies. We also use a lot of F#. Our backend is probably 90 or 95% F#. So we have sort of doubled down, and we are an F# shop, like a lot of folks say they're a C# shop. We have Node and Angular on our front end, our Python and SAS for our data science. And the green down here is sort of everything else we have. And we use some Xamarin, we use Kafka, Event Store, microservices, Puppet, Jenkins. We're, like I said, very much a right tool for the job company. So this does focus on F# and on how we make some of those, our services reactive. So the Reactive Manifesto, and there was an updated one in 2014. I don't know if there's been an updated one. But today's modern applications should be responsive, message-driven, resilient, and elastic. And I will go into what they mean for each of those. So responsive, almost every program has to handle events, whether it's clicks in the user interface or listening to sockets in the server. Events are really just a reaction to a change of state. And in F#, we have some really convenient features of events. They are immutable, so they don't change from underneath us. And concurrency of any form is wicked difficult if you're trying to handle immutable data. They all do implement iObservable. So events are values of type iEvent of T. They inherit from iObservable. And this is used in other libraries, the reactive extensions. Because of this, though importantly, they implement iDisposable so we can help prevent some memory leaks. They're also first class. So events, similar to functions in a functional language, events are values. We can pass them around as inputs. We can, in parameters and outputs, we can filter them. We can transform them. They are first class, and we can treat them like that. It's really very convenient. They're also composable. Not only can we filter and transform all of these, but we can compose all of the operations in the event module. So similar to this. Here we have a very simple and very real-world example of a program. But it basically loads up a little button. If you hit the button quickly, it'll only add 1. If you click it very slowly, it will add 4. Useful example. But you can see we have EV is our event that we're taking in. And we are transforming this. We're taking the event, piping it into an event.map, grabbing the date time. The scan is where we handle either the 4 or the 1. Then we're taking the first item and adding that on and printing out how many clicks have been set, and then doing an event add to actually set the text to show how many clicks have been handled. But we're able to compose all of these things, pass the event around as if it's just an ordinary parameter. You'll also notice all of the piping that happens in F#. And F# piping is huge. You will see it in almost every piece of code that you will encounter in F#, almost, not all of it. But it was so important to the F# community that when they created a new logo a couple years ago, they took their design from the pipe. So it's important. But mapping, scanning, and adding, as well as adding, choosing, filtering, these sorts of things are actually called combinators. We can actually create our own of these. And this here is how we would use a combinator that we've created called using, and the code at the top is how you would actually create that. But because we can create our own, we can, it's very extensible what we can actually do with events. So that was responsive. Message-driven is the fun part of this talk. So before we move on to message-driven properly, let's talk about async workflows. And what those are is really just an application of F# computation expression syntax. And which is, I will show you guys. So before we actually look at that first, let's talk about async versus concurrent versus parallel. A lot of folks, since we're going to be talking about async workflows, let's get that straight. Asynchronous is just non-blocking. Usually it's in reference to I/O operations. It can be something else, but it just means actually non-blocking. Concurrent means multiple operations happening at the same time. So they're not necessarily in parallel. It might be on one thread. It might be a little bit of one thing happening, and then a little bit of the next thing, and then a little bit of the first thing again. So they're happening basically at the same time, but they're not happening fully at the same time. Whereas parallel, they're actually processed simultaneously. So there's maybe two threads, and two things are happening at the same time. So the computation expressions now, since they're basically a mechanism that will execute a controlled series of expressions. So it's an evaluation of steps. There are a few things I am trying not to say here. They can be monads, and this could scare folks that are not familiar with functional programming, but they're actually more generic than that. They're not just monads. And that if you have seen, there's a famous example where folks compare monads to burritos, and that's how, famous blog post. But computation expressions aren't just a burrito. They're an entire buffet of food. There's all sorts of things you can do with them. It can be a monoid or an additive monad. So lots of different things, and you can come talk to me afterwards about what those actually are. But the point is, we can do lots of really cool things with them. So async workflows basically, simply make it really easy to work with async. It's very, very easy to convert. It ends up reading very similar to your classic linear code. And because of that, it's very easy to understand what's actually going on. So we take a simple example, create a new web client. We download some data based on a specific URI. And then we output the data length. Here, I have a slightly longer but very similar of a processing agent that starts in an async loop. And in this, while true, we have here. We have a new URI, and then we have this web client. And then we have an async download string. And at the end, we print out a set of information. The main differences here are that we need to actually have the async computation expression. So we need the async and the curly brackets around it. This is one of the few cases in F# where you will actually see curly brackets. And then we have a let bang instead of the standard let. In F#, let is how you sort of define everything, whether it's a value, whether it's a function. That's how you start. Let bang will start the computation immediately, whereas let within the async workflow will create an async object for use later. So the main differences between the top bit of code and the bottom are that it is in the async workflow. We have this let bang, and then we have an async download string instead of the download data, which is not asynchronous. So it is very similar. I mean, let web client equal new web client. The HTML is very similar, and then here we're using a printfn instead of an output stream write. But it's very, very similar code. And then what this would actually print out is, if we're Google, Microsoft, and MSDN, then those are sample numbers that we would be looking at. So within an async workflow, we generally have, we'll have a recursive loop around this, and have, here we're awaiting an event so that we can grab these clicks. We also have in addition to the let syntax, we have a do and a return syntax. They perform similarly. Async sleep is very similar to a thread.sleep, except it's obviously asynchronous. There's also a possibility of doing a back pipe. It's exactly the same as a front pipe, which if you folks have done PowerShell programming or any Linux programming, it's the same concept. You're taking the output of the previous information and passing that in as the final parameter into the next set of information. So that's how that back loop works. In general, backpiping is really only necessary if you're trying to avoid adding parentheses. So you could write async.startImmediate parentheses loop 1. So message-driven, since let's talk properly about message-driven. Message-driven is really done using the actor model in F#. So what that is, it's a model of concurrent computations using actors. The main sort of tenets of it, dynamic creation of actors, inclusion of actor addresses in messages, interaction only through the actual message passing, and no restriction on message arrival order. Thank you. Middle button, thank you. So the actor model was originally created it was modeled on well, it was first implemented in the programming language Erlang. And Erlang was first developed properly to be used with telephone systems, Ericsson telephone. And the concept of an actor model fits very, very nicely with this. One of the most famous folks who originally developed the idea said that one actor is no actor. And Carl Hewitt, I believe. And if you think about it, the idea of having one telephone is sort of useless. You can't really call anybody if you only have one telephone. You can't really do any. I mean, these days you could use your telephone for apps and other such things. But you can't call somebody. You can't text somebody else if you're using the only telephone in the world. So a lot of these concepts make a lot of sense if you think about telephones. Well, dynamic creation of actors, you can create more telephones and give them away to more people. Inclusion of actor addresses, you need a telephone number to be able to contact a specific telephone. Interaction only through direct asynchronous message passing. The only interaction with telephones, really, is through calling or maybe texting or maybe Bluetooth. But if we go with texting, the only interaction there is some form of texting there. It's not like one telephone can reach out and grab the other telephone and shake its hand. No restriction on message arrival order. Again, if you think about text messages, sometimes you go through a slightly dead zone and you come out and you get messages all out of order from one of your friends. So the actor model, actors themselves, the telephones you might think of, an independent computational entity, contains a queue and receives and processes messages. That's all they really do. There is this, you can think of them as basically a mini queue. Another way I like to think of the actors in the actor model is sort of like a subway system, or metro. This is actually the Tokyo subway, but you can think of each station as a single actor. The trains coming in are messages, and so you have, a message will come in, the actor will process it. Some of the folks will maybe stay on the train, continue on to another station. Some folks will get off and transfer trains and continue to a different section. And some folks will get off the train as their final destination. So that's the sort of processing that will happen for each actor. There's also some terminology. Actors are generally theoretical. Agents are often how Erlang refers to them and many other folks. Mailbox processors are what they're actually called in F#. For all intents and purposes, they are basically the same thing. There are some differences if you really want to get into the nitty-gritty, but basically, if you're trying to Google basics around them, they are good to go. So with actors, agents, and mailbox processors, but mailbox processors specifically, they use async workflows to be able to handle the message passing and processing. So here's an example. And so You have all of the agents here. We're creating 100,000 separate agents. And we have a mailbox processor. We're starting the implementation right away. We have an inbox, which is where the messages come into, obviously. And within that, we have an async workflow. Within the async workflow, we have our loop. Here we have a while true. We can have a more functional style loop if we need to. Both work perfectly fine. You don't have to strictly adhere to functional style. And again, we use our let bang to receive the messages. This obviously will wait until there is a message to receive. And then for every 10,000th message of the 100,000, just print, yes, I got a message. So it doesn't actually do very interesting processing here, but as a very basic example, it shows you the structure of how agents are, what should look. And then to actually post, we need to know, excuse me, for each agent in all of these agents, do an agent.post. So agent here is, excuse me, is the actual address of this agent, the telephone number that we're posting to. And then the output will look something like this. And these don't necessarily come in order. I've run this code sometimes and had 60,000 and 70,000 messed up. The other thing about agents is they're very, very lightweight. I can run this code and spin up 100,000 of them on my laptop. They're not threads. So they are much more lightweight. So there's a few more interesting things we can do with agents. We can actually get a reply back. So agents, as they stand, don't necessarily, you send a message off to it, and you may never hear from anything again. So for this example, we have our mailbox processor. We send in a string and an async reply channel of a string. So that gives us a way to have a reply. There's a channel through which we have this reply. Again, we're starting right away. And our inbox, this time we're using a recursive loop. And we have our async workflow. And here, when we receive the message, we have to receive both the message and the reply channel together at once. Then we can do a reply channel.reply. Yes, we actually received the message. This is what it was. And here, we're just continuing to loop. And then we're calling the loop. So instead of doing an agent.post, now we have to do an agent.post and async reply and send in an actual reply channel. So the important bits here are we need the async reply channel. We need to decompose it out of the receiving the message and then actually use it to reply. And then when we call the agent, we do a post and async reply. So obviously, this just repeats the message that was sent into it. Again, very real-world example. One more thing that's important to a message-driven setup is actually being able to scan an agent's queue. So here we have these two, and these two are taken from a very small app that basically uses a couple actors to simulate being able to monitor and then cancel jobs that are being created. So it automatically spins up about 10 of them and then holds some of them, holds all of them in the in-progress agent, and it's just it just holds them there. It doesn't actually process them in any way so that you can scan and see what's actually happening. But then you can scan and actually cancel some of them. So when they're completed, we have the same, we have our recursive loop, we have our async, we have an ID and a result coming in for the receive, and then the result of this. So this is what we'll print out when it's actually, when it actually finishes. For the actual cancel job, we'll contact the in-progress agent and do a scan, which basically scans the entire queue, sees what's there, and sees what options there are. Here, we just do a quick source.cancel, and if that actually exists, then run that action that we've just created. Otherwise, don't do anything. So if we find the job that we're looking to cancel once in this scan, then we will actually cancel it. And then, obviously, the important part here is just the scan. So one major difference from Erlang, the F# agents don't actually work across process boundaries. so only within the same process. In most cases that I have done, and this is coming from somebody who doesn't regularly use Erlang, using F# mailbox processors has been completely fine. It's been sufficient for our needs, but it obviously is not always. But there is a library, Cricket, which used to be called f#.actor, which does handle across process boundaries and some other really interesting things. So the way you use Cricket actually is very, very similar to the way that you would use just regular mailbox processors. Here we have just a greeter. It'll print hello world in a couple different ways. We have an actor instead of a standard async workflow. Then you have to specify a name for it, because actors need to have a name by which you can communicate with them. And then the body here will have, again, a recursive loop, which will handle the messages. It needs to have a message.receive, because you need to receive messages into your inbox so that they can be processed. And then processing section. So we're just doing a simple pattern match here. We're matching the message with either a hello, where it prints hello, a hello world, it prints as hello world, or a specific name. And then we run actor.spawn instead of actor.start. So, and the message type, obviously, is a discriminated union of hello, hello world, or name with a specific string. And then the way to call this is you call greeter with a back arrow and name, and it would print hello from F#actor. The way to handle remoting is calling actor_host.start. You subscribe to events, and then you enable remoting with, by setting up a TCP transport and TCP actor registry transport, and making sure you have your endpoints and your the registry discovery. So it's not that complicated. It's just a few actual lines to get that properly set up. And then you can do fun things like this. We have a ping pong game built with the two actors. So we have an actor here. This is just the ping actor. There's a similar pong actor. And they will just loop back and post, ping and pong and go back and forth to each other. But the actor internals are the exact same here as the non-remoting. So there is nothing different. We're still receiving a message. We're still matching that message with a pong, or it's receiving a ping message from ping, which is bad. Otherwise, in some other case where it's either not pong or ping, something is terrible and you should stop. But there is nothing here that's different when you're actually using remoting. So that's how you would handle message-driven. The next step is resilient. So resilient, as it says, the system should stay responsive in the face of failure. So one of the major tenets and points of Erlang is that it's self-healing. It can work with itself, know what sort of errors are happening, and try to fix itself. So this obviously is very important, especially to highly available mission-critical systems, but also to anything. If you have an app that's not responsive, that's throws errors all the time and can't figure out what's going on, it's very annoying and obnoxious to use. So error handling is an important part of being a resilient, responsive application. So here, we tend to want to use async. Tasks that are run using async run synchronously should report any of their failures back to the controlling thread. And specifically to do that, we'd want to use async catch. Async.start with continuations, which is another way of running an async workflow, also has an exception continuation. That's another really good way of handling exceptions within async. There's also a supervisor pattern, which is common, again, in Erlang, and very, very useful within the actor model. So async catch, here we have, not the most real-world example again, but this is really best for async workflows. But here we have we're doing an async start. We have two, we're basically trying to write to a file immediately after reading. And if we do this quickly enough, we'll still be reading the file. When the code comes to try to write to the file, it'll still be open. It should fail. And exception occurred reading from this file. You can't access it. So you try to call write to file. So first we call read file, and then immediately we call write to file, and we use an async catch and then an async run synchronously. And if there are either two options, either it successfully worked, which happens actually in most cases, or there is an exception because it went too quickly. But this is a good, quick way of handling an exception, from an async workflow. So async start with continuations. If you're using, for example, a reply, then this is a good way of handling that reply. So we have our message async here. We have an async post and reply, handling, gathering the reply channel. And then async start with continuations. We send in the message async, which is doing the post and async reply. And then we have three separate options. There's a continuation for a successful case. There's an exception for when, obviously, there is an error or something goes terribly wrong. There's also a cancellation case. So with the code that was running the jobs, this is the sort of handling that we would use. We'd have a cancellation option here, which would go and specifically cancel that job that was running. So another example for start with continuations, within the same bit of code, when we're actually doing the scanning, this is the agent that will actually start running. So from the same code where it double checks the starting the job. So it'll specifically start the job. It'll post to the in progress agent so that the agent is actually in progress. And then we'll call a start with continuations on this specific job. And first, the successful one, we have a complete agent. So we post to the completed agent when this has been successfully completed. In this case, we don't have an error. Clearly, nothing will ever error here. But with some good, and obviously this is non-production quality code. But here we would have a proper error handling here. And in this case, we have the cancel exception. So here's where we actually go out and cancel this properly using this token. And we loop around. But this is how we would use the start with continuations to be able to handle errors more effectively. The supervisor pattern. So for supervisors, when excuse me. When I first discovered agents, I wanted to solve every problem with agents. I thought they were very useful, very neat, and very typical developer response. I can do everything with agents. I wanted to write a quick sort of demo app, and the problem that we currently needed to solve at the job that I was at the time was how to handle all of the emails that we needed to both process and specifically send out. It was a company that handles helping brick and mortar grocery stores go online. So there were signing up and making sure your order was going to be delivered. There were please come back and order from us again. All sorts of very standard emails that you want to send out, and they needed to look a little bit different. So I wrote a quick demo with 5 or 6 agents, where some of them would handle a list of emails or types coming in, and people that needed to have an email sent to them, a template that the email needed to follow, and one agent that would actually specifically process all of the emails, one that would actually send them, and then this one, which would actually handle the erroring. So the error agent is, I aliased everything to agent. So the error agent is just a quick little agent that takes in a message that has both an integer and a system exception, and a specific agent ID, and an error message. And in the application, again, it was a quick little proof of concept. So that one's actually next, because I didn't actually read my code, and I switched my two examples. All right, I'm going to come back to this one. So in my email type, this is my error agent, and I have 3 different email types here, which makes a lot more sense. And type 1 might be thank you for your order. Type 2 is something else. But just, again, it was a proof of concept. And the point that I was going to go into, the proof of concept was the way I handled simulating errors was any email address that I needed to send to that had either an E and an N together or an A and an N together errored. No matter what, just to double check that I was handling all of the errors properly. So like I said, a very real world example. But here we're just handling, we have a message type, and this is how we're going to handle changing the, in one of the cases, I believe it's AN. Yeah, if it's AN, then if it has an E and an N together, then it fails permanently. If it has an A and an N together, then it replaces that and retries the entire process. So here's where we change the email. If it has an A and an N together, then we run the change function and actually change it, and then just return the message. So still within the error agent, now we come to our actual recursive loop, our async again. Here we're scanning the errors to see what's going on. So we first scan, and then we replace if we can, if that's, this is our action that we'll take. And we look at all of the data that we have, and we choose the specific one, and we do a replace AN, because that's how we fix our failure. And then we repost to the filtering agent, which will figure out which template it needs, and it will restart the entire process again. But basically, it's recovering from a failure automatically because we know exactly what error just happened. In the EN case, this is simulating something where we have no idea what just happened, and something actually went wrong, and we're going to need to actually go and discover that, log the failure, and come back to it later. So if the message contains cannot send, then specifically retry with an AN. If the message contains something about templating, then the issue is an EN, and it should fail specifically, and then run this synchronously. So the easier example with supervisors is a much more simple example where basically in this down here, if so for each of the agent we post, for each of these agents we post message to agent whatever with an agent ID. And we created a bunch of agents specifically. And so if the message contains agent 99, and we're creating 10,000 of them, so it's actually agent 99 and then 990 and 9,900, anything in there that actually ends up failing, or that actually ends up having agent 99 will specifically fail. Again, a contrived example, but we'll show you that if you understand the type of error that is happening, you can attempt to fix it. So up here, anytime that error actually happens, we just send to this agent error. We do an error agent.post, and along with the specific agent ID and the actual error, we call agent.start, and then rerun the whole loop at the beginning. So any questions on supervisors? Because I know that's a little much to get through. All right. So next we have Elastic. And this is very, very important. Elastic is one of the big important features of having reactive services, because the system really needs to stay responsive under a varying workload. At Jet, we have, Christmas season hits at some point, and people around Thanksgiving start buying everything on the planet, and the website comes under tremendous, tremendous load. And the same, well, not the same thing, but a similar thing happens, during the course of the workday. The load is a lot lighter at 9 a.m. than it is around 2 p.m. People get bored and start shopping. And, so you have to hit those after lunch blues somehow. You go out and make sure your groceries are handled or whatever you need, and then you come back to work for a little while. But we need to be able to handle all of this workload specifically. And so, reactive systems need to react to all these changes, increasing or decreasing these resources, and, automatically. So you need to know how to handle all of that. And especially with agents, it's very, very, very easy to scale agents on demand. So here, we're looking at a very similar example to the first example that we had, here in the middle, we have a processing agent. But here we have our actual URL list, and the square brackets is how you define a list in F#. So we have a list of tuples. So we have Microsoft.com, MSDN, and Google, strings of identifiers, and then strings of the actual URLs. Fun fact, when you list the items in a list out on their own specific lines, you don't actually need the semicolon. If you had listed those all on one line, then you still would need the semicolon. So we first have the processing agent. And this takes in a tuple for its message, which is going to be the string for the name and the URL. And for our inbox, we start it right away. And we have our inbox and our async loop. This time we're using a while true. Like I said, it really doesn't matter if you're using recursive or not. So we use our let bang. Here we're decomposing out both the name of the system and the URL. We're doing an inbox receive to get those. We're creating a specific URI from the URL. We're creating a brand new web client. And again, we're using let bang to asynchronously download the string of all of the information, the HTML on that page, and then excuse me, and then just printing out the characters that were read for the length of the HTML for that, read so many characters for a specific name. So the scaling agent then, if we wanted to do all three of these at the same time rather than running one at a time, or maybe we have a list of 500 websites that we need to get through, and that's going to take a lot more time to handle those all at once. Instead, we create this scaling agent that specifically, takes an agent, and then within our async loop, we have an inbox receive. We take the message that we've gotten, and then iterate through the whole list. So for each one of these items in the list, we create a brand new agent which handles the processing for each one, which just is an instance of this processing agent, and post the information to that new agent. So we're just iterating through each one of those. We could also, if you wanted to, make this an array and do an array.parallel and process those in parallel. But the point is, we're automatically spinning up a new instance of this processing agent for each item in this list, just as we need to. We could do this for, if there are 50,000 items in a list, we can spin up a new actor for each one of them, handle all of that asynchronously, and then come back. And it's a lot easier to automatically spin this up. And that's an important feature, again, of reactive services. And then from here, then we just post the entire list to the scaling agent, which handles the scaling for us by calling each one of the processing agents. Any questions on the scaling? Yes?
How is that different to just specifying 1,000 agents or something? Because you'd want a maximum limit on there eventually.
This will, if the URL list is a different size each time, then this will automatically account for that. So if you have 3 items in the list the first time and 1,000 the second time, then it's not necessary to spin up 1,000 each time. Yeah, it just automatically will handle that. And since I forgot to repeat the question, sorry, the question was just what the difference was between those. Anything? Yes.
What if we wanted to talk around limiting how many of those scaling agents we can have at each time? So if we have, say, a network and we've got 1 million in those lists, if we do 1 million HP requests across a firewall, we'll probably break the firewall. Is there a mechanism there that you can specify? Throttle. Thank you.
The question was, is there a mechanism to specifically limit those instead? You could do the same, specifically spin up an exact number. You could also, yeah, you could do another, like the list comprehension, the for agent in agents. You could do something like for 1 to 10 until the agents run out, or that. So yes, there is. I would say by using a list comprehension and just like setting a maximum and running through that until you've utilized as many as you need. There's not a specific built-in mechanism which I think is what you're looking for. So there are ways around it, but nothing very, yeah, nothing pretty. Any other questions? All right. I went a little bit more quickly than I wanted, so I was hoping you guys had more questions. So some general resources for F# specifically. Fsharp.org is a fabulous resource. There's all sorts of information on how to get started, on the foundation itself. The foundation is also running they're going to start back up soon, a mentoring program. They help out user groups. I know they have a speaker program, so speakers can go out to the different user groups. So if you guys either speak or run a user group or want to, definitely look into that. The Twitter #Fsharp is also fairly well monitored. Still, a lot of folks will jump in and if you hashtag something with Fsharp. #Fsharp. I have personally never tried it. Yeah, it felt weird to me, and then I discovered that people just spell out the sharp. So, yeah. That, as far as I know, that is not one that is monitored, is the #F hashtag. There is an Fsharp channel on the functional programming Slack. There is also one run by fsharp.org that I didn't list here. As soon as you join the organization, and it's free to join, you will get an invite to the fsharp.org Fsharp Slack channel, which is a really great resource as well. I would also highly, highly recommend Fsharp for Fun and Profit. Scott Blashen is, a fabulous speaker. If you haven't seen him speak, definitely go check out his videos. But even if you don't do that, go check out his website. He explains a lot of F# concepts, everything really, from very, very basic ideas to very, very complicated. Like he has a 13-part section on monads, I think. It's amazing. But even basically, like, why is it important that F# is immutable by default? So he hits all levels. It's very easy to understand, very, very, very good material. There's also F# Weekly. It's just a weekly blog post digest that you can get that lists out the latest, new releases of F# projects, new talks or blog posts that have come out lately. Just basically a weekly update of the F# community. It's a really useful resource to keep an eye on what's actually happening with the rest of the community. There's a few MailboxProcessors in general, a few really good blog posts here. The CSharp Async gotchas is, excuse me, is by Tomas Petracek. He wrote a blog post after one of his, and I don't remember which one of his trips to Microsoft, probably for an MVP summit, but to talk to, he was talking, there was a talk there on some of the folks by some of the folks I think that had worked on CSharp Async, and they were just going over a few, make sure you really understand what you're doing. If you think you're working with this bit of code, you could accidentally do this because it's a little unclear here. And Tomas went through in his blog post, and for I think each one of the things that they had presented in their talk, he went through and showed that basically the F# compiler prevents you from actually making any of those mistakes. And I don't, definitely go check out the series. It's a 2 or 3 blog post series. But in each case, or in almost every case, it's basically not possible to make that same mistake because the F# compiler cleans up after you and was like, wait a second, I don't think that's actually what you mean. Go check something else. Is that a question? Sure.
Hi, sorry, I'm actually quite new to functional programming. I'm getting my head around it.
Sure.
Obviously very strong and object-oriented. There was a previous talk about pure functions and impure functions and the testability of pure functions. Just wondering if there's the same kind of concept of like visibility, like private, public for all those functions, or, I mean, how do you protect a pure function so that the entire application doesn't access it and do what it wants with it?
You can set things as private. I tend not to as much because as an evangelist, a lot of the code I write is actually demo code. But it's absolutely possible, and it is obviously recommended in many cases. I know there's private, public. There's, yeah, I definitely, there are ways, absolutely. And I think almost everything actually corresponds to the C# ways, but don't quote me on that because it's been a really long time since I've actually looked at C# also. Anyone? Okay. So there is an F# control reactive project. Definitely check out the Cricket project as well. It's a really, really good. There's also additional actor library-based projects that also are really, really good and very well maintained within the F# space. I happen to show off Cricket, but don't take that as an endorsement of that over any of the others. But definitely go try to find the C# Async gotchas post. And that is it for me. If there are any other questions. Thank you very much.